Hey physicists, we're going to talk about a way of accounting for momentum. Remember that momentum is inertia in motion, and inertia we measure in terms of an object's mass, and that is measured in kilograms. Motion we measure by an object's velocity, and remember, velocity is speed with direction. Not just speed, but speed with direction. All right, so we'll end up measuring that in terms of, most commonly, in meters per second. It can be, left, right, down, up, but we do have to associate some type of a direction with that. Okay. Let's go back to the idea of momentum and how difficult it is to change an object's motion. Recording? Yes, it is. We know that heavier objects are more difficult to stop. Say I have a small car, and it's going along at, say, 10 meters per second. It's about 20 miles per hour. And I also have a large truck. There's a smokestack on that. Okay, but also going at 10 meters per second. That truck is going to be much more difficult to stop. Let's take a look in terms of speed. We know that faster objects are more difficult to stop. Take the example of two skateboarders equal mass. We have one skateboarder going along at 5 meters per second, the other skateboarder going at 1 meter per second. We know that it would be more difficult or change the momentum of the 5 meter per second skater. So we know that momentum, which is given the abbreviation P for progress, is a product of both mass and velocity. And so it has the units kilograms times meters per second with a direction. So right, left, we can call that. And for convenience right now, so we'll also say direction here, the convention is that we'll go to the right, will be the plus direction, left would be the minus direction. So I'm going to show you a little method to account for momentum, and that's going to be referred to as a momentum chart. Example 1, we're going to have a bowling ball. We have a bowling ball here, 3 holes rolling down an alley. Our bowling ball has a mass of 5 kilograms. Let's say it's going to the right at 4 meters per second. Okay. How can we account for that? A little graphic way of doing that. I'm going to put velocity on the vertical axis because that has both a plus and a minus. We're going to call to the right the positive direction. And then mass, because that's a scalar. Remember, it doesn't have a direction, it just has an amount, to the right. The way I'm going to represent momentum is the area of a rectangle. Okay, so let's take a look at that. Okay, so I have 5 kilograms, so I'll indicate that as starting here. 1, 2, 3, 4, 5 kilograms, and my velocity 4 meters per second, and that's to the right, so that's going to be considered a positive quantity. 1, 2, 3, 4. I can turn this into a rectangle. And so the area of this rectangle is proportional to the momentum of our bowling ball. To calculate it, give it a number. P is going to be equal to our mass times our velocity. Our mass is 5 kilograms. Our velocity is a positive 4 meters per second. So our momentum is a positive 20 kilogram meters per second. Let me do another little example here. I got a scooter Perhaps I got one for Christmas. Okay, and that's going to be going to the left this time. My scooter is not very massive. It only has a mass of about 2 kilograms, but it's pretty quick. It's going to the left at 8 meters per second. Let's see if we can account for this the same way on this momentum chart. Again, I'll put velocity on the vertical axis, positive and negative. I'll run my mass over this way. Now, an idea on this is that it's not really important where I start to mass. It doesn't have to start here, as long as I end up having a rectangle of a certain width. In this case, I'm going to have my rectangle is going to be 2 kilograms wide. So 1, 2, and then I want to make it 8 meters high. Now notice it's going to the left, so I have to call that negative 8 meters per second. So I'm going to call it 1, 2, 3, 4, 5, 6, 7, 8. Let's go ahead and draw a rectangle here. So it's interesting, my rectangle is 2 kilograms wide. It's 8, but actually negative 8 meters per second high. Let's see what our momentum is. P is equal to our mass times our velocity. Mass in this case, 2 kilograms. Our velocity, negative 8 meters per second. Momentum of our scooter is negative 16 kilogram. Oops, I'm just going to erase that for a moment. Let me just write it down here so you can see it better. Equal to negative 16 kilogram meters per second. Okay, let's go ahead and make a little summary on this. Okay, so up here we have our momentum definition. An important thing is that it has direction as well. Okay. Hey, we know that both more mass or more velocity gives us more momentum. Wish momentum was a shorter word. Let's see, we have our equation for momentum. We're using the symbol P for momentum. Is mass times velocity. Remember that that's a vector. And let's scroll down a little bit further. Hey, over here, let's take a look. We have our momentum charts. And the area of those rectangles is our momentum. I think that pretty well summarizes it. Maybe our last thing down here, if we want to put a summary, just a couple of sentences about this. And our summary is that momentum, which we give the letter P to, is inertia in motion. Inertia in motion. Sorry about the handwriting. And is the product of mass and velocity. Important thing, it has direction. And the units are the kilogram meter per second. As I probably have mentioned, that's up for grabs. Last item here are momentum charts. Momentum charts are drawn on a velocity versus mass graph. Velocity has both a positive and negative value. Mass is a scalar along the horizontal axis, and it graphically shows the momentum expressed as P by their area.